This is the video on waves. So remember, in these videos, there's going to be two codes. There will be one code that will pop up on the screen, and the other code will be a verbal code said by myself at some point in the video. So remember, when you're looking through this video or looking at the slides that accompany this video, right where it's in green, that's a nice way to make a nice little bulleted list of what is the important in there. The rest is just going to be good, important information that could help you out. Just that extra information. So write what's in green. All right, so this is the written code. I would recommend writing this down somewhere. All right, so this whole thing is about waves. The question is, what is a wave? Well, a wave is a mechanism for transporting energy from one location to another without transporting matter. So think about waves in an ocean. So you can see that it appears as if the water is moving across the water, right? It appears as if it's, but the water molecules aren't necessarily moving with the water. And you can see in that top one up there, you can see that the water molecules don't really move far away, but it is transporting that energy across the ocean or lake or river or pool or any of that body of water. So let's take a look at the different parts of the wave, right? So for this video, we're going to be focusing on those transverse waves, the ones on the bottom, longitudinal waves, very similar, just a little additional things, but we're just going to look at the transverse wave. So if we're looking at the different parts, the crest is the top of the wave. The trough is the bottom of the wave. The amplitude is the distance from the origin to the crest. And you can see these are labeled, right? Crest, the top. The trough is the bottom, the amplitude top to bottom, and the wavelength is the length of one complete cycle. So you can see in that picture, it's labeled crest to crest. You could do trough to trough, you could do origin to origin, but you have to be careful, make sure you're measuring from the origin going up to the origin where the wave is going up as well. Otherwise, you're only going to get half the wavelength, right? But the wavelength is just the length of one complete cycle. It's just a lot easier to measure crest to crest. So all of these, like you could look at this and you can measure these with like a ruler or a meter stick, right? These are all measurements of some sort of length or distance. Now, when we're talking about time, we need to talk about frequency and period. Wave frequency is the number of waves that pass a fixed point in a given amount of time. The unit is 1/seconds, more commonly referred to as the hertz. Frequency is basically cycles per second. So if you look up there, 3 hertz, 3 cycles in 1 second, 6 hertz, 6 cycles in a second, 12 hertz, it's going to be 12 cycles in a second. Now, the wave period is the time it takes for that wave to complete one cycle. The unit for the period is seconds. We're just measuring, hey, once it's one complete cycle, how long does it take? Frequency and period are the inverse of each other. So you can see here we've got different graphs. The top one is like measuring the distance, and then down on the bottom, that's the one where we can measure time, like the time. So there's two different ways to graph waves. So here's how I like to view frequency versus period. They are inverse of each other. As frequency increases, the period must decrease. As period increases, frequency must decrease, right? One goes up, the other goes down. One goes down, the other must go up. That's what inverse is. And you can see the period, 1 divided by the frequency. The frequency is 1 divided by the period. So here's a good example of frequency versus period. A hummingbird flaps its wings back and forth 50 times a second. Right? So if we're looking for the frequency, that's how many cycles per second. That's going to be 50 hertz, 50 cycles per second. Now, if we're looking for the period of the wing flaps, that's how long does it take that bird to flap its wings once. So it's going to be the inverse. The frequency is 50 hertz. The period, the inverse, which would be 0.02 seconds. So just a little fun little fact. That might seem fast, but the hummingbird is the fastest bird that flaps its wings, but it's not even close to how fast a wing can move. So there are some insects, and there's one there that's pictured there. It's 1,460 hertz. So that'd be 1,460 cycles per second, right? So that's incredibly fast. And if I wanted to find the period, I just take the inverse, 1 divided by that. It's going to be very short because that's measuring how fast that insect can flap its wings once. All right, so wave speed. Wave speed is basically how fast that wave is traveling. Now, this is sort of the key, and I would recommend highlight this, star this. Wave speed depends upon the medium that the wave is traveling through. We measured in meters per second. So you can see up here two different graphics that could help you out. The top one just shows I'm going from a faster to a slower medium. And you can see that the wave speed changes. And I'm going to go ahead and put my cursor up on top of that. And you can see that, it's moving, certain speed, certain speed. Then it's going to hit another medium. Then it's going to slow down. It's going to slow down. Now down here at the lower, let me just shrink this so you can see a little better. Like we're talking about sound. Sound travels a lot faster in solids and liquids than it does in gases, right? So you can see that it does depend on the medium. So that brings us to this question. Why is it hard to find the direction of a sound underwater? And it all has to do with how we interpret sound. How we interpret sound is our brains measure the time difference between sound hitting one ear and the sound hitting the other because it's traveling a distance. Now, the speed of sound in air is 343 meters per second, and our brains are tuned to that because, I mean, we live, on land, and we're walking around, and we measure sound, within the air. But the speed of sound in water is about 5 times faster, 1,482 meters per second, right? So our brain just cannot interpret that difference in time. To us, it sort of feels like it's instantaneous. So if you're underwater, like in a pool or a lake or an ocean, and someone like making a noise or like banging on like something metal, you're going to have a very difficult time trying to find the direction of the water or of that sound. And it's because our brains just aren't adapted for that, right? Now, or over 4 times faster. Now, let's see, plants as well, sound of Mars. So if someone is deaf in one ear, and this happens too, if someone's deaf in one ear, they have a hard time determining where the direction of that sound is coming from because they only hear the sound, right? And they don't have that benefit. And like they don't have the benefit of being able to tell the difference in time. So you can see that graphic up there does show that. So let's put all this together in the wave equation. So you can see here that it's basically let's look at the variables. The variable v is the velocity of the wave measured in meters per second. We just call it wave speed. The variable f is the frequency and is measured in hertz. And the variable, this is the lowercase lambda. So it's the wavelength of the wave and is measured in meters. So when changing medium the wave speed changes, right? The wavelength will change, but the frequency is going to remain the same. So you can see here, this is a good one changing from medium. I'm going from a faster to a slower medium. You can definitely look at this and tell, okay, great. I know that the wavelength changes because the one on the left, a lot longer, one on the right, well, it's definitely a lot shorter. Now, this is how you can measure the speed. You just put your hand or your cursor on top of one of these waves and you can just move it across. Now, once it hits another medium, well, you'll definitely be able to feel that it's going a lot slower. Now, the frequency is going to remain the same, right? Changing the medium does not change the frequency. It changes the speed of the wave, and because the frequency remains the same, that wavelength changes too. And I can tell the frequency remains the same. It's kind of hard to tell from here, but if you put your cursor in the same spot and just sort of count off, like the beats, right? So every time a crest hits, just count. So 1, 2, 3, 4. I can do this over here. 1, 2, 3, 4. You can see that I'm counting at the same rate. The frequency is the same, right? So that's what it is. And this equation, you can use that triangle to calculate whatever you need to in that equation. If we look, we did a couple activities this week. We did the wave simulation. This is a very good simulation where you can set up a wave and you can measure all the different aspects of it. The purpose of this activity was to see how all of them affect each other. What affects the wave speed, right? If I change the wave speed, what affects that? And it made some really nice graphs. It was a really great way to get in there, time some things, a really great way to get in there and like measure the distances and lengths of certain aspects of a wave. Next up is the wave problem. So we actually got practice using that. That wave equation. So at this time, I'll go ahead and give you the verbal code. The verbal code is 246. I say that again. The verbal code is 246. So once again, in this, really good practice, setting it up, finding the equation, finding the known variables, and then calculating that unknown variable. The last thing we did a lab. Everyone loves a slinky. In this one, what we were doing is we were measuring how fast waves travel in a slinky. We were stretching that slinky out, and we were sending a pulse down. And that pulse was going down and back, and we were timing how long it took, and we were calculating that wave speed. What we were doing was we were increasing the tension in that slinky, which is changing the medium. Now, when you change the medium, the wave speed should have changed. So once again, just as a final thought, remember there's too much unknown in the universe to take a break from learning. Get out there and question everything.